Okay, good morning, Pak Juliadi and my friends. Thank you for coming to this presentation. And I would like to share about making process of pre-cutting steel from scrap by using electric arc furnace, ladle furnace, and continuous casting machine. And before we start the presentation, let me introduce our member in this group. There are 9 of us, which are Mutia Fahira, Sultan Fahrudin, Alif Abdul Rahman, Putu Rizka, Erika Danitra, Alvin Sains, Yamanda Cynthia, Fikri Nurul Salah, and the last is Teresia Santoso. Okay, there will be four major parts of this presentation. The first one is scrap, the second one is electric arc furnace, the third one is ladle furnace, and the last is continuous casting machine. And let's begin with the first topic, that is scrap. This is process route of making uh, steel, pre-cutting steel. And the first image, it shows us that external scrap will be sorting and preparing before chopped into the electric arc furnace. And then in the electric arc furnace, the scrap will be melted, and there will be refining process as well. And then there is like controlling process before the hot metal is stepping into the ladle. And in the ladle, there's also advanced refining such as deoxidize and desulfurize. And then there also alloy addition to adjust the cutting steel. And then in continuous continuous casting machine, the steel will be cast into the long product to fulfill the consumer needs. Steel scrap. Steel scrap consists of discarded steel or steel products, generally segregated by composition and size or grade suitable for melting. There are uh, three main types of scrap which are used by the steel industry as feedstock. These are internal scrap, from scrap, and obsolete scrap. The first one, internal scrap, also known as reverse or home scrap. It refers to the reject metal within the steel plant, which gets generated during steel making, steel casting, and steel finishing activities within the steel plant. From scrap, also known as process scrap, and it is the waste generated during the product manufacturing by the steel plant customers. And the last of solid scrap consists of the scrap which is recovered from discarded industrial and consumer items, such as from ships to refrigerators and from construction bin to automobiles. The difference between these three scrap is internal scrap produced from steel making plant, um, from scrap is produced from manufacturing plant, and obsolete scrap is produced from consumer or discarded industrial. This is the chemical composition of several scrap. Uh, in the chemical composition of scrap, there is a tram element that is not expected to be charged into the electric oscillate. So we should do some preparation to remove or to minimize the tram elements such as nickel, molybdenum, and copper. So this is the scrap sorting and preparation technique. The numerous source and form of ferrous scrap require the use of numerous scrap sorting and preparation techniques to remove the contaminants or recover other valuable materials prior to entering the steel making process. And the first type of sorting is manual sorting and preparation. Manual sorting obviously involves the removal of components from the scrap by hand. It is most suitable when miscellaneous attachments have to be removed from the scrap or when manual offloading is unavoidable. So the separation of metallic from non-metallic is also often accomplished manually. For large items such as ships, automobiles, appliances, railroad cars, and structural steel must be cut using shear, handheld cutting torches or cutters to allow them to be chopped into the furnace. The next step is scrap size reduction process, and a wide range of equipment is used to reduce the size of large scrap material into pieces small enough to enable consolidation, fixation, and subsequent feeding into finish. The first equipment is rolling press. Loose scrap that has a high surface area and low density must be compact by bowling or bucketing. Bowling press is a heavy piece of processing equipment that uses up to 3 hydraulic drums to compress the scrap that requires greater density before remelting. This equipment is usually operated by dealers and processors who prepare, who prepare the scrap to be fed into the steel mill. So the bowling press equipment is can be seen in the below. The second equipment of size reduction is briquetter. In a briquetter, in a briquetter, small scrap is compact into pockets as it passes between two counter-rotating drums. Compaction can be achieved with heat depending on the material. So the image in the above is the product of briquetter scrap. The third equipment is shear. The hydraulic guillotine shear slices heavy pieces of steel, including I-beams, steel plates, pipes, and railroad car pipes. Okay, the next one is shredding. Shredders or fragmentizer can reduce old automobile hulls into fixed-size pieces using massive hammer. The shredding process produces three types of material uh, that are ferrous metal, light fraction shredder residue, and heavy fraction shredder residue. The two residue fractions, either singularly or collectively, are frequently referred as automotive shredder residue or ASR. The next equipment is magnetic separator. Magnetic separator is used when a large quantity of ferrous scrap must be separated from other materials. Magnetic separator is used permanent magnetic and electromagnetic. Magnetic separation can be of either the belt type or the drum type, and in the drum type, a permanent magnet is located inside a rotating cell, and material passes under the drum on a belt, and a belt separator is similar except that the magnet is located between pulleys around which continuous belt passes. Magnetic separation also has a limitation. It cannot separate iron and steel from nickel and magnetic stainless steel. The next equipment is eddy current separation. Eddy current separation are used to separate non-ferrous metals from waste and ASR. The process generally follows the primary magnetic separation process. by passing the magnetic current to the lead ring and using recursive force interacting between magnetic field and the eddy current is in the metal. The simplest application of the process is the inclined ram operation. The process on the below is on the scene. Okay, the last step of steel scrap sorting and preparation technique is the coating technique. The main source of zinc is galvanized steel with scrap, and the removal of zinc using thermal method can be accomplished using various techniques such as the galvanized rods are heated into a high temperature more than 900 degrees Celsius, at which the zinc evaporates. And also can be the galvanized parts are heated to a temperature sufficient to unravel the coating, which is then removed by ablation. And the last heating and subsequent removal of the coating is accomplished by shot blasting. And for deadening, cindering scrap in steel recycling affects the surface quality of the steel product because tin segregates to the grain boundaries and causes surface gaps during working. Some of the processes being used for deadening the tin plate scrap include an electrolytic and alkaline deadening. And the last is incineration. Some scrap processors use incineration to remove combustible materials, including oil, grease, paint, lubricants, and additives. Okay, this is the look of scrap preparation plan from car scrap. So the process is begin with this machine. This is a press machine, so the car will be charged into the press machine and pressed to a smaller size or smaller piece, and then feeding into a conveyor and charged into shredder, and in the shredder, the smaller piece of scrap will be crushed, so the scrap will be even smaller than the press, and then the product of shredder machine will be charged through the magnetic separation to separate the non-ferrous metal and ferrous metal. The ferrous metal will be stored in the scrap yard and ready to charge into the electric arc machine.
Okay, next I will explain about electric arc furnace. Next. Electric arc furnace is a furnace that heat charged material by means of an electric arc. This electric arc furnace usually used for scrap steel making. This furnace was patented by Carl William Siemens for steel making. On the right side, this is a picture of the electric arc furnace where there are 3 electrodes, refractories, pipe, fuel gas, and etc. This furnace usually use electrical energy as the main energy and usually used to process scrap. Next. Okay, this is a type of electric arc furnace. Basically, electric arc furnace is divided into two, namely direct current electric arc furnace and alternating current electric arc furnace. This is a picture of DC and AC electric arc furnace, there are some different DC and AC electric arc furnace. In DC electric arc furnace, use one graphite electrode, and AC electric arc furnace use three graphite electrode. Next. This is DC and AC electric arc furnace that we can look this next. Okay, this is the difference between DC and AC electric arc furnace. First, component top electrode, DC electric arc furnace has one graphite electrode, and AC electric arc furnace has three graphite electrode. And the bottom electrode, DC EAF installed in the refractory, and AC electric arc furnace not needed. And the power source, DC electric arc furnace is direct current, and AC electric arc furnace is alternating current and three-phase. And the rectifier, DC electric arc furnace, needed to convert AC current to DC current, and AC electric arc furnace not needed. Next. This is electric arc furnace construction. Basically, electric arc furnace split into three sections. First, the shell, which consists of the sideways and lower steel bulk. And second is the heart, which consists the refractory that lines the lower bulk. And the third is roof, which may be refractory line or water cooled and can be served as a section of a spare or as a frozen. The roof also support the refractory delta in the center, through which one or more graphite electrode enter. For the more complete in the picture, more explain the part of electric arc furnace, like number one is furnace shell, number two is furnace or slaking door, number three is tapping spot, number four is roof, etc. Next. This is a shell electric arc furnace construction. We use magnesia-based refractory to lining the furnace. In slag, there was zinc or carbon. Why we use magnesia refractory? Because in this process, the condition is oxidative, that FAO is very dangerous for refractory, and the temperature is very high. In the top of the shell, we use a water cooling panel to cooling the furnace. In this panel, be careful, because if the panel leak, it can ruin the process. And the panel made by boiler steel plate. And the roof of electric arc furnace full of cooling water panel to cooling the roof, and the center is alumina based refractory. Next. Okay, this is a graphite electrode. The graphite electrode is used to transfer electrical energy from power supply to the furnace. Electrode most capable to withstanding large temperature and chemical aggressivity during furnace operation, at the same time providing continuous and uniform power supply to the process. Next. Okay, this is a typical properties of graphite electrode. One, apparent density about 1.63 or 1 until 1.77, yeah. And the specific electrical resistance about 4.5 and until 5.5, and flexural strength about 9 or 8 until 15, and thermal conductivity is 160 until 300. And the coefficient of thermal expansion is 0.3 until 0.7. Next. This is a furnace operation. In electric arc furnace operates as a batch process. In the operation of electric arc furnace, basically in 16 minutes. One is first charge is 3 minutes, and second is first meltdown is 20 minutes. Second charge is 3 minutes. The next is second meltdown is 14 minutes, and the next is refining 10 minutes, tapping 3 minutes, turnaround 7 minutes, and total is 16 minutes. Next. This is the main step in electric arc furnace. First is charging stop, charging scrap, melting, addition some reagent, select and decarburization, and finally is tapping. Next.
Okay, my name is Baga. I will explain about the process that happen in electrical arc furnace. The first step in electrical arc furnace is charging the scrap into the electrical arc furnace. This is the type of raw materials that can be charged to electrical arc furnace. We can use scrap or direct reduced iron or maybe pig iron or hot metal, and we can uh, charge that into electrical arc furnace. But for now, we will focus on and we will assume that all the raw material is from scrap iron. The specialty of electrical arc furnace is when we use this type of furnace and we use raw materials, it has no limitations in how many percentage of scrap iron that can be charged. Uh, and that is advantage of using electrical arc furnace. Next. The most common way to charge the raw material into electrical arc furnace is using proper metal bucket. As we can see in the picture, that is the metal bucket that is used to charge the material into the electrical arc furnace. The bucket is simply a vessel with an opening below to dump the material into the corresponding furnace. And we can see in the picture also that the bottom part of the bucket is open, and it indicates that the material are being charged into the electrical arc furnace. In order for the scrap to enter the furnace, first the roof and the electrode in the electrical arc furnace are raised and then swung out to give an opening for the scrap to enter. After the opening are open, the opening in the bucket that holds the raw material will be opened, and the raw material will be entered to the electric arc furnace. After the material is charged into the electrical arc furnace, the roof and the electrodes are swung back and lowered to close the electrical arc furnace. This charging process is not done by only one time, but will occur 2 to 3 times in one heat. Why this is happening? Because the electrical arc furnace has specific capacity that may not enough for the total scrap that will be melted in one heat. So the charging process must be done 2 or 3 times. Uh, the concern of this charging by bucket is there will be that time or time when the electrical arc furnace is not having power and not melting. This that time will decrease the efficiency of the total product of the electrical arc furnace process. So we must find a way to decrease the charging amount in one heat. Next. As we can see, this is the example of charging process. The big bucket in the top is the bucket that used to charge, and the below part is the electrical arc furnace. We can see that the opening in the bucket is already open, so it will charge the material into the electrical arc furnace. Next. This is the optimal distribution of scrap into the charging bucket. So charging the scrap material into the electrical arc furnace cannot be done in a wrong way. There is some consideration to make the next step or the next process in the electrical arc furnace made easier. So in general, heavy scrap or scrap with high density is taking more time to melt than the light scrap. So in the charging process, we must arrange the scrap according to its density. In the top, we must uh, place the light scrap so it will melt faster and form a liquid steel faster. And the liquid hot steel will transfer heat through convection to the bottom part of the charge. Then below it will be placed medium scrap and heavy scrap. So why we use heavy scrap in the bottom? Because it will avoid graphite electrodes to be damaged by the liquid steel. So we can use mainly the heat from the liquid steel that has already melted and the arc from the electric arc furnace. And the bottom part is light scrap to preserve the integrity of electric arc furnace bottom and decrease placing of hot heel. So that is the charge consideration. Next. By the disadvantages of the bucket charging or batch charging, there is some method of scrap charging that is invented. As we can see in the picture, it is from Consteel. Uh, we can see that it is continuous charging. So it is not using a bucket that needs to be charged and it be turned around, but it is using a conveyor uh, that will move the scrap into the electrical arc furnace. We can see there's scrap yard, then the conveyor that will move the scrap to the electrical arc furnace, and then there's preheating tunnel that use the carbon monoxide gas that is produced in the electrical arc furnace to preheat the scrap, and then the scrap will enter the electrical arc furnace. Next. Now we will focus on the bucket charging method or the batch method, and this is the material balance in electrical arc furnace. It is not exactly the material balance like in the scrap, but how many percentage or how many weight is the component in the electrical arc furnace. You can see that the electrode is 1 to 3 kilograms, dust is up to 20 kilograms, of gas is up to 250 kilograms. There's steel that contains to 1 ton of steel, and there's refractories, slag, and many more components that build the electrical arc furnace when it's charged. Next. The next process after the charging process is melting process. As we know, the electrical arc furnace is one of many tools that are used in metallurgical process to melt materials. So melting is the core of the electrical arc furnace process, which can be done by supplying energy to the furnace. We can see at the first picture there is a short scheme of how melting process is done. First, there is after the electrode and the roof are lowered and set into the electrical arc furnace, the electrode will lower even further, so it will bore into the scrap. It will melt the light scrap that is in the top of the electrical arc furnace, and it will dig or bore into even deeper part of the electrical arc furnace, and it will melt the scrap even further. We can see then there is after boring there is stable melting when it's already reached the lowest part of the electrical arc furnace, and then the scrap will begin falling into the hot liquid steel, and it will continue and it will melt all the scrap in one charge down to all liquid steel. After this has been done, the process will be repeated into the charging step again. Why we doing the charging step again, as I said before, is to reach the designated amount of liquid steel that we want to melt in one heat. After that, after there is a stable line of liquid steel, we will do refining, which will be discussed next. Electrode, as we can see, is the main contributor or largest contributor in melting the scrap material. The electrode will provide or supply the electrical energy to melt the scrap. This electrode will melt the scrap by radiation from the heat from the arc, and then the radiation will melt the scrap, and the molten scrap will transfer the heat through convection, and then the heated scrap that is not melted yet will transfer the heat with the conduction. Next. Beside electrode, there are oxy-fuel burner, which is supplying chemical energy to melt the scrap. Oxy-fuel burner, as we can see in the process, it looks like torch. It will burn the scrap material to evenly distribute the heat into the scrap, so it will melt evenly. Because if we use arc, it will only heat, or it will mainly melt the scrap that is below the arc. And then the oxy-fuel burner can also reduce the cost of steel making, because using oxy-fuel burner is cheaper than adding the electrodes. So if we want to increase the efficiency, there are two options, which is increasing the number of electrodes that used, or adding another alternative method to melt the scrap. So oxy-fuel burner is one of the best option to increase the efficiency of steel making in electric arc furnace. Next. So this is the process of the melting that I said before. First, it will be boring of the electrode into the bottom of the electrical arc furnace until there is stable melting, and the scrap will fall into the uh, molten steel, and it will melt all the scrap down in one charge, and it will charge back again 2 or 3 times until the amount of liquid steel that desired is reached, and then the process will continue to refining. After the melting, next, after the melting process, we will continue into refining process. What is refining? Refining is a process to remove impurities in the metal. In the melted product, generally the impurities are phosphor, silicon, carbon, aluminum, silicon, and manganese. Removing these impurities can be done by oxidizing these compounds. Basic oxidizing slag composed of lime or calcium oxide and iron ore or ferroxide can be added to oxidize these impurities, but sometimes oxygen can also be blown into the furnace to oxidize even further. How to blow oxygen into the electrical arc furnace? We can use the oxygen lens to lens the oxygen into the bed, so it will have high amount of oxygen that might oxidize the compounds that is impurities in the steel. We can see, we can take an example of how ferroxide or FeO is used to oxidize the impurities. It will the ferroxide will form oxide that will help oxidize the carbon, the silicon, mangan, phosphor, and aluminium. So the bracket itself, as we can see in the reaction, indicates different stage or different place of the compounds. As we can see, the square bracket indicates solution in steel, the curly bracket indicates in gas phase, and the round bracket indicates that in slag. So we can see the silicon oxide, manganese oxide, phosphorus oxide, and aluminum oxide is all will go into the slag, and carbon monoxide, that is the product of the oxidizing, will go into the gas phase. The first we will see into the phosphor. Low phosphor level is needed in certain steel. If we make some certain steel, there is level of phosphor that is allowed in the final steel. So we must remove this phosphor by making the phosphor oxide, by oxidizing the phosphor, and we will remove them in as lowest temperature as possible. Why is that? I will explain in the next slide. But we will back to the manganese. The manganese will be lowered into approximately 0.06% in the refining process, and the carbon is lowered by making them into the carbon monoxide gas. This carbon monoxide gas will help to strip the nitrogen and the hydrogens, and this process is called decarburization. This gas or carbon monoxide gas is also used to make foam in the slag, or we can say that it's like foaming, and we can use this carbon monoxide gas also to preheat the scrap that will enter the electrical arc furnace if we use continuous charging method. Next. In the end of the refining, the sample are taken. I'm sorry, I forget to mention that. And moving on, we will first see additional process that happen between the main electrical arc furnace process. As we know, the main process is charging, melting, refining, and then deslagging and tapping. But there's some process that occurs in between those process that helps increase the efficiency of the process and reduce the waste that may harm the environment. Our main concern here is slag foaming. What is slag foaming? Basically, the slag foaming is we injecting the gas into the slag, so it will rise the slag with foam, so it will cover the electrode and give some advantages that will be mentioned later. Slag foaming can be done by injecting oxygen to foam up the slag, or injecting carbon so it reacts with peroxide. The injection of carbon or oxygen is intended to create carbon monoxide gas that will foam up the slag. We can see that is the scheme in the picture about how the oxygen is injected into the slag and how it will form the foam in the slag. Next. This is the advantages that we can get if we do this process or slag foaming. First, it will protect sidewall from arc radiation. As we know, the longer the process gets in the electrical arc furnace, the amount of the liquid molten steel will increase even more. If this continue, it might damage the sidewall from the arc radiation, because the arc is not stable in the higher temperature, so it might damage the sidewall. By making this slag foam, it will prevent the arc from damaging the sidewall. So next advantage is enhanced efficiency of post combustion. What is post combustion? Is basically combusting the excess product that is not combusted perfectly, such as carbon or any other gas that is not combusted perfectly. And then the dust emission will reduce. The nitrogen content is also reduced because the carbon monoxide gas is higher in the electrical arc furnace, so it will reduce the nitrogen, and then the arc stability will increase because it is there is a slag foam that will help the arc to stabilize, and by stabilizing the arc, that means there will be less flickers and less noise, and energy transfer into the melt is higher because the slag foaming can also transfer the heat via convection through the scrap that is not melted, and it is possible to operate with long arc, which means the electrode does not have to enter the arc furnace deeply. It just need to uh, enter the electrical arc furnace deep enough so it will touch this slag foam, and then the slag foam will help transfer the heat. Next. Back to the main processes. After refining, as I said before, this sample are taken to see the composition and the temperature in the electrical arc furnace. Is this as we decide or not? If not, we will have to longer the process, and we have to remove the slag so it will not go back into the steel. As I mentioned before, phosphorus have to remove in the lower temperature as we can, because in a higher temperature, it will the phosphorus oxide that is inside have a chance to react with the phosphorus oxide needed to be taken out as early as possible in the lowest temperature as possible. So after we do refining and making the impurities into the oxide form and making them into the slag, the deslagging process is done to remove the slag. Next, this is the picture. This is the picture of the deslagging process. As we can see, when the deslagging process is done, the electrical arc furnace will be tilted into the back to make the slag go into the back opening, which will throw the slag into the dump to the waste. So the electrical arc furnace will be tilted to the back to dump the slag, but not tilted enough to make the steel also dumped by this um, opening in the back. Next, after we take a sample again, so basically after the deslagging, we will take the sample again to see are the compositions are as we decide or not, or the temperature is as we decide or not. But the temperature is not a problem in nowadays steel making process, because we can also increase the temperature even further after the electrical arc furnace. So the main reason we take a sample is to check the composition of the steel that we make. Once the desired spill composition and temperature are achieved in the furnace, the tap hole is open. So in electrical arc furnace, in the back there is a slag hole, and the front there is the tap hole. This tap hole is used to dump the final product in the electrical arc furnace into the next step, that is ladle furnace. In this process, the oxidizer may be added to the steel to lower the oxygen content prior to the further processing. This is commonly referred to as killing the steel, because we will reduce the ferroxide by adding some deoxidizer. So it will be referred as the killing the steel. Common deoxidizer is aluminum or silicon in form of ferrosilicon or silicon manganese. After that, the slag forming, there will be slag cover that is built by the tapping process. This slag cover is good, especially when it's calcium aluminate, because it is good for the sulfur control. Slag forming compounds are added in the ladle at taps so that the slag cover is formed prior to transfer to the ladle furnace. So basically, when we transfer the liquid metal into the ladle, it will form a slag, but some type of slag that is formed in this process is beneficial to sulfur control, such as calcium aluminate. As we can see, this in the picture, in the left side is a tap hole that is located in the centric bottom tapping, and the right is the siphon tapping. The main difference is in the location of the tap hole, where the centric bottom tapping uh, is located in the bottom of the electrical arc furnace, so it will require less tilting, and the siphon tapping has a tap hole in the front, so it will require more tilting. Next. As we can see in the picture, there's a example of tapping process in the industry, which is the electrical arc furnace will transfer the molten steel into the ladle furnace. So in the picture, we see that the type of the electrical arc furnace that they are using is the siphon tapping, because it has a tap hole in the front and it needed to be tilted into certain angles or to certain degrees, so it will transfer the liquid steel. After this tapping process, the liquid steel will be continued to the process to be processed by the ladle furnace. But for the electrical arc furnace itself, will be turned around to be prepared for the next charging and for the next heat. This turnaround is the highest dead time, which means the electrical arc furnace has no power and not melting. So what we do when we turn around the electrical arc furnace is we do raise the roof and the electrode, and we will inspect if there is any damage that has been done to the electrical arc furnace prior to the process that has been done before. After that, the electrical arc furnace will be repaired if necessary, and if not, it will be prepared for the next charging process and will be prepared for the next melting step. Next. Well, that is the end of the electrical arc furnace.
Okay, the next process is carried in the ladle furnace. Next. First, LF specification and supporting tools. In the right, we can see the layout of ladle furnace operation. Our ladle furnace consists of ladle with capacity of 100 tons, transformer to modify the electrical energy of the power station into the required condition, network used to connect all systems, electrode lifting and lowering device to lift and lower the electrode when the operation starts and finish, ladle lid and ladle lifting and lowering device used to lift and install ladle to fit into the furnace, heating bridge frame, steel ladle, ladle carrier to carry the ladle, and wire feeder used to feed the wire when allowing process occurs. Next. The next specification and supporting tools is argon regulating system to inject argon into the ladle, water cooling system used to control temperature in operation range system, compressed air system, hydraulic system, temperature measurement and sampling system to control the temperature and ladle composition during the process, automatic charging system used to charge automatically so that the process is more efficient, high voltage power supply used to match with electric energy required during the process, and the last one is low voltage control system with aim to control the whole process in LF. Next. So this is the technical parameters used in the ladle furnace. Because our capacity is 100 tons, we use LF100 model. LF100 model has ladle cell inner diameter of 3.6 meters with 100 and 100 max in capacity. The capacity required in this model is, the capacity of transformer required in this model is 18 million volt ampere, which is the calculation will be shown in the further slide. Then we use 5 degrees Celsius per minute of heating rate. The graphite electrode diameter is 450 millimeters, and the circle diameter of electric center is 740 millimeters. Next.
Now, one of the main purpose of ladle furnace is for the oxidation process, which is used to decrease oxygen content in metal, especially after oxygen increase because of oxygen blowing or decarburization in electric arc furnace. As shown in graph on the right side, that with the decrease of carbon, there will be an increase of oxygen. For the oxidation process, in ladle furnace, we use the oxidizing agents such as ferromangan, ferrosilicon, or aluminium, which will react with oxygen in metal to form mangan oxide, silicon oxide, or aluminium oxide. Mangan, silicon, and aluminium is used since based on Ellingham diagram shown on the left side of the screen. Mangan, silicon, and aluminium are located at the bottom part of the Ellingham diagram, which means that they react pretty easily with oxygen thermodynamically speaking. Next. Now, how do we choose what the oxidizing agent to use? How about the effectivity of each reducing agent? To answer this question, we need to take a look at the three graphs shown on the screen. As we can see, aluminium is capable of producing metal with the lowest oxygen content in metal with just a little bit addition of aluminium. On the other hand, with relatively lots of addition of ferromangan, the oxygen content produced in metal is still much higher than aluminium. And for ferrosilicon, the oxygen content produced in metal is moderate or between what we can produce by using aluminium and ferromangan. That's why for ferromangan, the steel produced is still called unkilled steel, for ferrosilicon is called semi-killed steel, and for aluminium is called killed steel, since the oxygen content has been reduced to a really low percentage. In industry, usually the usage of ferromangan is accompanied with the addition of aluminium, and this is not a really effective and efficient process since when mangan react with oxygen to form mangan oxide, it can collide with aluminium and react to form mangan and aluminium oxide. But then, even though aluminium can produce the lowest oxygen content, the addition has to be evaluated strictly since there is a possibility that aluminium will result in inclusion in continuous casting machine process. Aluminium can be added around 0.03 until 0.04%, where the oxygen content is already relatively low enough to minimize the possibility of inclusion. Next. Now, as we know, slag contains oxides such as ferrous oxide, mangan oxide, and silicon oxide. When these oxides interact with the oxidizing agent, they will react and therefore reduce the effectivity of the oxidizing agent since the oxidizing agent did not react with the oxygen in metal. Therefore, we need to get rid of these oxides by using agents such as calcium carbide, silicon carbide, aluminum shot, or ferrosilicon. Next. Not only to decrease oxygen content, ladle furnace can be used to decrease sulfur content in metal too. Top slag is used to reduce sulfur to anionic sulfur with the help of flux like calcium oxide, which will react with sulfur to form calcium sulfide. Reducing agents such as carbon, silicon, and aluminum is also added to react with the oxygen from calcium oxide so that there will be no increase of oxygen content in metal. To predict the sulfur content, we can use the KTH model, which is shown on screen to calculate the sulfide capacity of slag. From the sulfide capacity value, we can calculate the LS or the sulfur distribution in slag compared to sulfur in metal. A good desulfurization process is when we can get the highest LS value possible, but of course we need to consider the ternary phase of calcium oxide, silicon oxide, and aluminum oxide to maintain slag in the liquid form. Next. There are two types of desulfurization, one with cord wire injection and the other is with powder injection. The process principle are basically the same. One of the main difference is that cord wire use porous plug for steering using argon, while in powder injection steering using argon gas is done by the same injection lens used for the powder injection. Powder injection is usually produce a lower sulfur content and therefore is more favorable. Next.
Next is alloying. Alloying process is required to adjust steel molten composition specifications. Table 1 is showing required compositions of steel molten. The following compositions must be fulfilled before the steel molten is transferred to the continuous casting process. Alloys that needs to be added are ferrosilicon, ferromanganese, and lead wire. If the carbon concentrations of EAF hot metal already close to specifications, then the carbon content in alloy that will be used must be considered. Meanwhile, sulfur and phosphor content are regulated through the desulfurizations and phosphorizations process. Next. Temperature. Temperature will change if we add some alloying element into it. The additions of high carbon ferromanganese gives a temperature reductions effect for about 25 degrees Celsius, while the additions of ferrosilicon will increasing the temperature of the molten metal because the reaction is exothermic enough. Besides that, there's temperature reductions due to purging gas process for about 1 until 2 degrees Celsius per minute. To eliminate the temperature drops, heat is supplied by using ladle furnace with 5 degrees Celsius per minute heating rate. Ladle furnace is equipped with transformers. This is the calculations of rate capacity of the transformer. It shows that we need 18.25 megawatt to supply heat for the ladle. This calculations is matched with technical parameters of ladle furnace in the previous discussions. Next. Why we should control the inclusions in molten steel? Inclusions modifications process has to be done to clean the inclusions which can decrease the mechanical properties and corrosion resistance of the steel. First method to decrease inclusions is by using synthetic slag. The functions of synthetic slag is to move oxides that have the potentials to become inclusions into the slag. The additions of synthetic slag also provides a layer that limits the contact of the molten steel with the environment so that it can reduce the oxide swarm, which has the potentials to become new inclusions. There are several types of synthetic slag compositions that we can use. And based on this diagram, the best type of slag is type D that contains 55% calcium oxide, 10% magnesium oxide, 50% alumina, and 20% silica. Next. And next method is powder injections. We can modify the inclusions by adding calcium to molten steel as a powder injections. The calcium as calcium silica form will modify the aluminium that used for aluminium kill steel in the oxidation process. By soft bubbling process, alumina will move into slag layer so that it doesn't become into new inclusions. And last one is using nozzle. Charging process from ladle to tandis is using throat or refractory nozzle, as well as casting process from tandis to mold is using sand or submerged entry nozzle. And the functions of both nozzle is to minimize the oxidation process during charging.
Okay, so how do we control steel cleanliness? Okay, these are 5 types of operation to aim clean steel. First, adding calcium carbide or aluminum salt to reduce the amount of oxide in the slag with rustite plus manganese oxide below 2%. Second, metal or slag mixing. High stirring energy required in initial process to get chemical equilibrium between metal and slag, dissolution from alloy, and agglomeration of inclusion. Third, adjusting slag composition to optimum level to get slag with low oxygen content and low silica. Fourth, trying to avoid adding the oxidator in the end of LF process. And fifth and final is doing soft bubbling for about 10 minutes. Next. And we have the final ladle composition, and the composition is 0.11% carbon, 0.1% manganese, 0.1% silicon, 0.065 phosphorus, 0.26 sulfur, and 0.25 lead. Then the ladle is transferred to the further process, which is CCM, or continuous casting machine. Next.
Hello, my name is Alif, and I will explain to you about continuous casting machine. Continuous casting machine, or CCM, also known as strand casting, is the process where a metal is heated until it liquefies. The molten metal is then allowed to solidify until it becomes a semi-finished slab that is later rolled in the finishing mill. It is used to cast metals of uninterrupted lengths. In this process, the molten metal is continuously supplied to the mold. The mold has indeterminate length. When the molten metal is cast through a mold, it keeps traveling downward, increasing its length as time passes by. The molten metal is continuously passed through the mold at the same rate to match the solidifying casting. This result is in casting of long strand metals. The whole process of continuous casting is precisely the deliberated process that can produce astounding results. So as we can see in the right picture, the molten metal at the ladle, and then at the molten metal at the ladle will go down to the tun dish, and then at the tun dish, it will continuously supply the molten metal through the mold. This mold at the right side, it will shape the metals, and then it will go downward until it solidifies and cooling. CCM has several advantages. Continuous casting is a method that was invented to enhance the production of metals. The continuity of the casting helps to lower the cost of the casted steel. Further, it helps in the standardized production of steel cast. Further, the carefully controlled process also reduces error, leading to better quality steel cast. They increase the productivity and produce better yields. Continuous casting eliminates some of the problems of traditional casting method. For example, they eliminate piping, structural and chemical variation that are common problem of ingot casting method. All the casting products manufactured by continuous casting process uniform properties. The solidification rate of molten metal is also 10 times faster than the solidification of metal in ingot casting method. So, in the table below, in this one example of the continuous casting specification, it can produce product thickness from 150 until 300 millimeters, and the solidification time is more than 600 seconds, and it has casting speed of 1 to 2.5 meter per minute. An average heat flux in the mold is 1 to 3 megawatt per meter square, and it has metallurgical length of more than 10 meters, and melt weight in the caster is more than 5 tons. Another advantage of CCM is this process is cheaper than rolling. It's 100% casting yield. The process can easily mechanize, and thus labor cost is less because it's and thus labor cost is less. Casting surface are better. The grain size and structure of the casting can be easily controlled, and it has high production rates. While it has so many advantages, CCM also have some disadvantages. Continuous and capable cooling of mold is required, else centerline shrinkage will develop. Only simple shapes can cast, which should have a stable cross-section. Large capital investment is necessary to set up process. Because of large capital investment is necessary, so it's not proper for small amount of production, and it requires large ground space. This is some types of the CCM. So different continuous casting processes exist to produce cross sections of different shapes and size. This is the types of products that produced by CCM. So like when I said in the disadvantages, it only simple shapes. Only simple shapes can cast. So this all of this is only a simple shapes. Heavy four-piece plate molds with rigid backing plates are used to cast large rectangular slabs, which are rolled into plate or sheet. Similar molds are used for casting relatively square blooms. This bloom on the left upper side. Single-piece tube molds are used to cast small square billets. Piece tube molds are used to cast small square billets, which are rolled into long products such as bars, angles, rails, nails, and axles. The new strip casting process is being developed using large rotating rolls as the molds will solidify 1 to 3 millimeter thick steel sheet. So this is the types of CCM depends on their molds, and with different molds, it casts different shapes. Now, and this is another types of CCM, but this is about the machine differently. Vertical machine are used to cast aluminum and a few other metals for special application. The vertical machine is the most left, and curved machine are used for the majority of steel casting and require bending and or unbending of the solidification strand. It's in the middle one. And the horizontal casting features a shorter building is used occasionally for both non-ferrous alloys and steel. It's on the upper right side. And finally, the thin strip casting is being pioneered for steel and other metals in low production markets in order to minimize the amount of rolling required.
And then next is this is equipment of continuous casting machine. This pictures of the configuration of continuous casting machine. There are several equipment that needed for this CCM machine. The first is ladle turret that represented by number 1. This is the system that can rotate the ladle into the casting position above the tandis, so the process can run continuously to supply molten metal to tandis below. Then number 2 is the tandis, located above the mold, to feed liquid steel to the mold at regulated rate, typically between 1.5 meter per minute to 2 meter per minute. And the number 3 is mold, to produce steel in particular shape. And then number 4 is a primary cooling zone or water-cooled copper mold, through which the steel is fed from the tandis to generate solidified outer shell that is sufficiently strong enough to maintain the strand shape as it passes into the secondary cooling zone. Number 5 is strand guide. In this area, also called as a secondary cooling zone, that association with a containment section positioned below the mold, through which the steel, mostly liquid, the strand passed by roll support and is sprayed with water and air for further solidify the steel. And then number 6 is straightener withdrawal unit. Number 7 is dummy bar disconnect roll. Number 8 is severing unit. This is a cutting torch or mechanical shear to cut the solidified strand into the piece of further processing. Number 9 is dummy bar storage area. In this area, dummy bar and steel are separated. Number 10 is cross transfer table. For transfer to identification system. Number 11 is product identification system, to identify the product whether it contains defect or not. And then the last is number 12, product discharge system. And then this is a picture of ladle turret. This is the system called as turret that can rotate the ladle into the casting position above the tandis. So the process can run continuously to supply molten metal to tandis below. And then this is the several type of tandis used in industry. The shape of tandis is typically rectangular, as shown in the top of picture, but delta and T shape are also common. Nozzles are located along its bottom to distribute liquid steel to the mold. The tandis also serve several other key functions, such as tandis can enhance oxide inclusion separation through several actions that can be done, such as using a long nozzle, both from ladle to tandis and from tandis to mold, and then installing the tandis plugs on the top of tandis to case inclusion, and then introducing argon gas into the tandis to encourage the inclusion to react with the plugs at the top of tandis. And then tandis also can provide continuous flow of liquid steel to the mold during ladle exchange. Maintain a steady metal height about the nozzle to the mold, thereby keeping steel flow constant and hence casting speed constant as well for an often furing metering system. And also provide more stable stream pattern to the mold. And then this is tandis car used to move the tandis from the preheating process to the CCM machine, or from the CCM machine after the casting process to the preheating process. And then this is the shroud nozzle. This is the schematic picture of nozzle that used for flowing molten metal from ladle to tandis, and also from tandis to mold below. Inside the long nozzle, there is a slide gate to adjust the amount of molten metal that will be flowed both from the ladle to TANDIS and from TANDIS to the mold. There is also a gas inlet for entering gas such as argon for the stirring process. This nozzle also have a function to protect molten metal from air oxidation. And then this is a schematic picture of the mold. The main function of the mold is to establish a solid cell sufficient in a strain to contain its liquid for even entry into the secondary spray cooling zone. And then the key product elements are shape, cell thickness, uniform cell temperature distribution, defect-free internal and surface quality with minimal porosity and few non-metallic inclusion. This mold usually made from copper. And then this is a mold oscillator. This is to provide an oscillation mechanism to the mold. The mold is moved up and down so the flux powder or the mold flux can enter and coat the mold surface as a lubricant. This is a schematic picture from ladle, TANDIS, and mold of CCM to produce a free cutting steel in the form of long product. The source is from Yoshimura. The title of this paper is Method of Manufacturing Leaded Free Cutting Steel by Continuous Casting Process. And then this is a dummy bar. The dummy bar is used at the beginning of process of pouring molten metal into the mold. That function is to hold the molten metal from falling directly to the bottom section, but undergo a cell formation process first in the upper section. This dummy bar also have a function to adjust the casting speed. And then is the torch cutting machine. The function is to cut the solidified strand into a piece for further processing. And then next is this is a production and feasibility study. This is the first step in the designing of continuous caster. First, the product and use dictates the quality, grade, and shape of the cast products, such as billet, bloom, slab, beam blank, or round. Considerations are then made based on desired annual tonnage, liquid steel availability, and anticipate operating hours. Then the machine design consideration can be made for the number of strands and cast speed to match the liquid metal supply from the melt shop. And then quality and grade consideration are then utilized in determining various design parameters of the casting machine such as its length, vertical height, coupe or straight mold, water versus water, air secondary cooling, electromagnetic steering, and others. This is the main technical parameter in continuous casting machine. The continuous casting machine model that used for this project is coupe continuous caster type, and then secondary cooling category uses is aerosol cooling, dynamic water distribution. Product type that produces a pre-cutting steel in the form of round, and then the product dimension is 500 millimeter in diameter, and then for ladle capacity is 100 ton. Mold length is 900 millimeter, and then mold oscillation frequency is 1.36 hertz. Mold oscillation amplitude is 60 millimeter. Metallurgical length is 39,200 millimeter. Casting speed is 1.5 meter per minute, and the number of strand is 1. And then time to time a ladle with assuming that timing stop at level of 5% of molten metal in the ladle is 43.6 minutes. And then this explanation about pre-cutting steel product. And then before explaining this pre-cutting steel, it is worth to classifying them in a wider context that is not very commonly found in the literature. From this picture in the right, we know that the pre-cutting steel is one type of special steel. In more detail, is the type of structural steel. According to what has been previously mentioned, pre-cutting steel are steel that have easy machinability characteristic. These steel are defined as the most suitable for machining process such as longitudinal and turning, toothing, drilling, reaming, or fashion that are performed in multi-spindle and full turning lathes. Pre-cutting steel in general are steel with carbon ratio ranging from 0.07% to 0.6%, and the sulfur ratio from 0.15% to 0.4%, and phosphor ratio from 0.07% to 0.1%. And this is the example of recutting steel product from some plate steel industry that have certification of quality that listed here, such as inclusion rating, microstructure, and other. There is also international specification of recutting steel from several country. That is from ES or Indian, BS from BTC, and from British, IC from American, GIS from Japanese, DIN from German, and ESTM from American. From this, we can see that each country has its own chemical specification. For example, from India, the minimum carbon content in pre-cutting steel is about 0.08%, but from British, there is no minimum carbon content requirement.
Continuous casting of pre-cutting steel. My name is Mutia Fahira. I'm 125-16009, and this is my presentation. Continuous casting of recutting steel. High sulfur steel alloy produced by continuous casting methods such as strand casting with higher amounts of sulfur up to about 0.65% can be added to improve machinability without including the deleterious effect of iron sulfide. It has been found that by forming the alloy in a continuous casting process, a dense uniform distribution of small particles of manganese sulfide can be produced. These particles will provide a material with excellent machinability. And the next one is the methods of continuous casting for producing a free cutting steel. First, pouring the molten alloy having the desired chemical composition from all ethyl into the tun dish of a continuous casting machine. Next, introducing the molten alloy continuously from the tun dish into the continuous casting machine mold with a desired cross-section. And thirdly is, additional techniques may be used to further refine the alloy steel produced and improve the machining characteristic. As the molten alloy is introduced into the oscillating mold of the continuous casting machine, aluminum wire may be fed into the mold to the coarse grain level. To achieve the coarse grain level, typically 0.002 until 0.008% to minimize pinholes and oxide inclusion in the long product. And nextly is continuously protecting the casting stream from the atmosphere to prevent reoxidation leading to pinholes and oxide inclusions. 5. Cooling the illuminated metal body so as to solidify the metal body. And 6. Continuously withdrawing the cooled metal body from the continuous casting machine. There are several concerns in continuous casting for free cutting steel. One of those is free oxygen concentration. A continuous casting is performed by transporting the molten steel after complete LF refining by deheating to a continuous casting machine. The free oxygen concentration of the molten steel is measured after starting the continuous casting, and this is for finding out in advance whether cuttability of the free cutting steel is good or bad. The free oxygen concentration is measured at a point of time about 10 until 50% of total casting time, and at this time the free oxygen concentration is sufficient if it is in the range of about 50 until 150 ppm. If the free oxygen concentration is measured when the casting time is less than about 10%, it is difficult to obtain an accurate free oxygen concentration due to effects of Tandish refractories or Tandish insulation materials. If measured when the casting time is more than about 50%, it is disadvantageous because of the opportunity to enabling the control oxygen is lost. Also, when the measured free oxygen concentration is less than about 50 ppm, cuttability is relatively poor according to experiments. On the other hand, when the concentration is more than 150 ppm, it is not good because pinholes and blowholes in long product are somewhat increased. In the continuous casting of the free cutting steel, a very long product or flap or billet may be obtained if an electronic steering device of a mold, like a mold chromatic steer or EMS, and a soft reduction device are operated. It is advantageous to obtain spherically shaped in large size M&S inclusion if the mold EMS device is operated. This soft reduction device is very advantageous to reduce center segregation of the long product.
and surface defects such as pinholes and blowholes at the surface of the long product. And that's our presentation about manufacturing free cutting steel from scrap until finally produce long product. Thank you for your attention.